As the limits just keep going and going and going and going. So we're talking about limits about infinity and how they're related to asymptotes and other things we know from precalculus and rational functions. So the last thing we look at with limits are those involving infinity. So there's two parts to this lesson. The one where there are going to be infinite limits. So like x is going, so in this case it's going to be like x is approaching plus or minus infinity. And then we're going to break this up into vertical, horizontal, and oblique asymptotes. I will say the ones we're going to focus on today are going to be the horizontal and the oblique, and the vertical ones we'll talk about in the next lesson. Well, not the next lesson, but the next day that we meet. Okay. So one thing to keep in mind when it comes to limits is our base example here is going to be with this reciprocal function. So let's go ahead and phrase kind of this idea here where we have these arrows pointing to the left or to the right in terms of limits. So let's go ahead and just do the right one first. So again, the graph continues. So we have the limit as x approaches infinity of 1 over x. So I've now phrased that idea of this going to the right in terms of limits using this function. To figure out what it's equal to, you can't just plug in infinity because infinity is not really a number. It's a concept of continued growth. So what we're basically going to be thinking about is like, okay, we start at 1 over 1, we get 1. Then if we were to go 1 over, let's say, 10, you would get 0.1. Then you would have 1 over 100, then you would have 100. And remember, limits are kind of like the pattern, like what's happening to these numbers if we were to continue? Where are these numbers heading? They're getting smaller and smaller and smaller. They are heading to the y value 0. And we actually had this idea back in precalculus a little bit. If you just kind of continued getting closer and closer, or if you continued going to the right, you'd end up getting closer and closer to the y value of 0. You won't ever hit 0 because you have the ideas of asymptotes, but that is how we would go ahead and work with the limit. So the limit here is equal to 0, even though we're never going to actually be equal to 0. But we're getting really near it, hence limits. The other arrow is over here. I'm going to color code this one in green. So to phrase this left side in terms of limits, we would just say the limit as x approaches, well, we're going to negative infinity of 1 over x. And that same thought process that we looked at above applies. Like you have 1 over negative 1, 1 over negative 10, 1 over negative 100. And if you continued this pattern, you're just going to get really close to 0. You won't actually ever be equal to 0, but you're going to get really near it. So we can say that the limit as x approaches negative infinity of 1 over x is equal to 0. And I've already kind of stated this a few times, if you look at what is happening right here, notice that 1 over x has a horizontal asymptote of y equal to 0. And again, I'm not trying to be funny. Okay, I am a little bit, but I'll just shorten this to horizontal asymptote instead of saying, or I'll shorten horizontal asymptote to ha. Ha. So little jokes here, little ha's all over the place. But now that we have this idea of how to look at these as x goes to positive or negative infinity, we can go ahead and kind of fit this idea of finding the limits in graphically to all of our other scenarios. So down here at 1, some of these are a review, some of them are new. But let's go ahead and look at A. The limit as x approaches 2 of f of x. Well, notice this is what we're used to. We approach 2 from the left or the right. We translate those to the graph. And, well, does the limit exist here? Yes, it does. And what is it equal to? it is equal to 0. The y value that we're approaching is 0. We have, in the case of B and C, our one-sided limits. So if we look at this time we're approaching -3 from the left-hand side. So in this case, what is the one-sided limit? It is going to be the -2. When we approach 3 from the negative, or the left-hand side, we see that we do have this little bit of a jump discontinuity. The reason for the jump discontinuity is because from the left-hand side, what limit do we find? It's a +2. So you can see right here, we have a jump discontinuity. And because the limits exist, but they are different, what can we say about D, the two-sided limit? We simply say it is D-NE, or it does not exist, D-NE. All right. So if we look at E, we have this other approach of a one-sided limit, and you can see if we approach it from the positive or the right-hand side, the y value we're approaching is -1. F is a little bit different than what we've encountered so far, though. The limit as x approaches 0 from the left-hand side, if you get really close to x equal to 0, and you kind of look at where this graph is going, well, this one is just going to infinity. Not beyond. Well, actually, beyond. It doesn't matter. So this one right here is going up and up and up. So this one goes, okay, so I'll say it like this. It is going up to infinity. What y value are you approaching? Well, your y values are just growing. So you would say the limit is equal to infinity in terms of the notation we have so far. Technically, since the limit is a number or a y value, it would be a little bit weird to say that it's equal to infinity, because infinity is not a number. But it does describe the behavior of the function going up here. Yeah, question?
So, I get it's infinity, but why would it not be described as does not exist or going up, like as a vertical asymptote?
Yeah, so technically right here, you could say that the limit, let me write it like this, because that's what I was starting to describe. But we could say technically the limit does not exist because the limit is a number and infinity is not a number. It's a description of behavior. So in the context of this one right here, we're really saying this right here more as equals to infinity as a description of the behavior of the function, because, as you pointed out, it is a vertical asymptote. So, and we're going to explore that idea a little bit more probably on Monday, just because it's going to take some time to do from horizontal asymptotes. So whenever you see this infinity, let's go ahead and call this out here. So when the limit is equal to an infinity, we have a vertical asymptote. So that's why we're calling it specifically out as infinity here, is describing the behavior of the function, growth upwards. So we have a vertical asymptote here. We'll just say what it is x equal to 0, the value that we were approaching. Does that answer your question?
It does.
Great question.
Sorry.
No, great question. I was trying to explain it, and I think you just gave me a better kind of jumping point. Appreciate it. Any other questions on that one? We'll explore that one more next time. But you still have this idea, because the limit does not exist right here. We have this differing. The -1 differs from the infinity, so you would say the two-sided limit does not exist. Kind of the same idea, that it approaches different things from different sides. And then H and I, it's waving to you. It's saying hi. Okay, bad joke. If we look at this, these are associated with your horizontal asymptotes. So if you look at the one going to positive infinity, we're looking at the y value is approaching as it goes to the right. The y value it is approaching right there is 1. And when you are looking at it going to the left, so negative infinity, what y value are we approaching as the x values go to the left? Anyone? 0. So kind of taking the same idea that I wrote here in red, but this time talking about it in terms of infinity. So when x is equal, or let me say this, when x is equal or approaching plus or minus infinity, this is either going to say we have a horizontal asymptote or oblique asymptote. So oblique. Also sometimes referred to as a slant asymptote, depending on your background. I think the pre-calculus here described it as oblique, but it's just the slant. So it's a linear function. More on that. We'll do an example later. So that is basically the graphical representation of limits. In this example, kind of all summarized, you will have something like that on the test where you're given just a general graph and you just have to say, okay, what is the limit as x approaches 0, or what is the limit as x goes to infinity, et cetera, et cetera. Any questions on this first example? Awesome. So now we're going to go ahead and focus more on the algebraic approach of horizontal asymptotes and limits as x approaches plus or minus infinity. So evaluating limits at infinity, good news, all of the limit laws are true when we replace the finite value with an infinite value. So the sum of the product is the sum of the limits is still the limit of the sum, et cetera, et cetera. So we're going to look at two kind of our base examples to help us figure out the more complicated ones. We've already talked about this one on the right on the first page. The limit is 0. It's your asymptotes. Again, you can also visually see this one if you want to. If you have your reciprocal function, just remember that it is in the first and third quadrants, and you have the asymptotes approaching 0. Doesn't matter if it's plus or minus. What about the limit as x approaches infinite plus or minus infinity of k? And maybe to clarify, k is a constant here. What was the limit of the constant? Is just going to be the constant. Very good. So the limit here is just going to be k. So in this first example, you just could go ahead and consider each little piece of this function and just find the limit of each part. So the limit as x approaches infinity of 5, well, that's the constant. So it's going to be equal to 5. And what is the limit as x approaches infinity of 1 over x? What did we say? 0. So the limit here is going to be equal to just 5. But we don't really have the idea of just plugging in a value here. We have the kind of this conceptual understanding of like the limit of the constant is a constant because it's just going to be horizontal, it's never going to be changing. And we have the idea of asymptotes to help us out. The other thing that I want to make sure you hold on to, like this 1 over x, just to maybe state it one more time, maybe a little more, I want to be a little more explicit this time. When the denominator is growing, realize the fraction as a whole is getting smaller. So again, like 1/2, 1/3, 1/4, so on. The denominator is growing, the numerator is fixed, therefore it is getting smaller and smaller. So that idea is maybe a little bit easier here. Let me go ahead and maybe show it the long way, but then I'll show you the short way. Or maybe a more conceptual approach to think about it. Let's look at number 3. You could go ahead and just break this limit up as x approaches negative infinity of pi square root of 3. And then you multiply that by the limit as x approaches negative infinity of 1 over x times the limit as x approaches negative infinity of 1 over x. So you can break that up as the limit of the product is the product of the limits. So if you did do that, you could just go ahead and say, okay, what is this first limit? The limit of pi radical 3 is pi radical 3. Then you multiply that by this limit right here. These are the same, so it would just be equal to 0 times 0, which ultimately the limit is 0. So if you were to just break it apart based off of the ones we already know, you could do that. But I want to make sure that you start to get a certain idea in your head. If you think about this right here, this is a constant. Does a constant function grow or get smaller? No, it stays the same. It's a constant function. We call it that for a reason. So, but if you look at the denominator, you can see what is happening to x squared. It is going to just grow and grow and grow. It's going to keep getting bigger and bigger. So while this is a little bit more complicated than 1 over x, the same principle applies. The top is going to stay fixed. The bottom is going to keep getting bigger and bigger and bigger. And when you have a numerator that is going to be fixed or a constant, and you have a denominator that is just going to grow, basically that's another way to think about the limit is just going to be 0. Because you're just going to get smaller and smaller and smaller values. So this computation a little bit tedious. Focus also on the conceptual understanding of how the functions are interacting. So go ahead and take a moment and look at 5 and 6. I'm going to take attendance really quick while you try, not 5 and 6, numbers are hard. I told you, explorations wore me out today, I'm just kidding. They were a fun class. Try 4 and 5 while I take attendance and see what you get. All right, let's go ahead and look at these together. So on number 4, let's see, anyone think they know the answer? Anyone think they got it? Emma? No? No? Sarah? You got a 1/2? Do we have any votes for 1/2? Ah, there you go. Very good. That is correct. It is 1/2. Because again, if you look at each part of this individually, the limit of the constant is 1. This right here, the limit of that constant is 2. And then again, that last little piece right here, we know that this is just going to be 0. So when all is said and done, we have the answer of 1/2 and a fairly colorful problem. Very good. Any questions on 4? Yeah.
Why don't you flip like the 1 over x to like the x on the infinity?
So if you wanted to do this, you could go ahead and do some algebra. The reason, well, you'll see here in a sec. Basically, this is our goal form when we're working with limits at infinity, because we can see that reciprocal function that we know how to work with. Initially, this could have been given to you as, let me convert this, so it would be 1 over 2x plus 1 over x, which is then x over 2x plus 1. So this one's a little bit harder to think about in terms of limits, because you have the x in the top and bottom. And if you think about this one, like okay, x is a linear function and 2x plus 1 is a linear function. So even when you talk about their growth, they're growing really close to each other. So that's, again, why we're going to get some idea of asymptotes, and namely a horizontal asymptote of 1/2 this time. So again, there are connections to asymptotes, and we'll make those connections in case anyone forgot them. But this is kind of the form that my math lab is going to tell you to get to. I'm going to show you kind of some shortcuts, though, as well. So, yeah. Let's talk about number 5 also. Anyone think they know the answer to number 5? This one's a little bit harder. Any volunteers? Weston?
0.
It is 0. Very good. How many got 0? Good, a couple people. Very good. So the reason it is 0, and this one's really kind of hard to conceptualize in terms of like, you can't just plug something in, but if you think about what is happening when you plug values of x into this one, basically this sine of 2x, this function is just going up and down. Well, that's cosine, so let's do sine. So that's going up and down. So this one is basically stuck is -1 to 1. Like, as you plug in different values, it's just going to oscillate. It's a trig function. It'll oscillate up and down between -1 and 1, where this one is just going, it's getting big. It's like it's big, it's growing. So if you have something that's, even though this is not constant, you have this idea that it's between -1 and 1, where this one is still going to be growing, and it's going to eventually just overshadow what is above. So again, that idea that your denominator is going to grow faster than your numerator is going to tell us that our limit here is equal to 0. Is that how you thought through it, or do you have anything to add? Awesome. I just wanted to explain it for everyone as well. Does anyone have any questions or any comments or any thoughts about 5 they want to talk through really quick? Awesome. So again, conceptually, it does require a little bit more kind of mental thought processing to say, okay, the top is between 0 and or is -1 and 1, where the numerator is growing without bounds. So you do want to be careful with kind of the limit there. So this will also relate to the question about kind of getting the compound fractions and getting rid of those. My math lab is going to explain this a certain way, and I'm going to go ahead and make a connection from some previous ideas that'll make the view and examples a little easier to understand. So this is essentially the process that my math lab is going to recommend in the view and example, and it's technically the proper approach, but I think that we can rely on some former knowledge to help us out. In order to find the limits of rational functions, we're going to divide every term by the highest power of x in the denominator. The highest power of x, and then this statement continues to the next line in the denominator. The line y equal to b, I've kind of noted this earlier. Whenever we get when we're considering plus or minus infinity, this value, this limit that we get is this y equal to b is going to be a horizontal asymptote of the graph. So when you consider x as it approaches plus or minus infinity, the limit is the constant that's associated with the horizontal asymptote. So let's go ahead and look at number 6. I'm going to go ahead and show you kind of the steps that my math lab's going through so you aren't confused by it when you see it. But then I'm going to remind you of a quick property of rational functions that'll make everything easier. So on number 6, like I said, it's going to go ahead and say on my math lab, multiply everything in the numerator by, hold on. What is it? How did I word up here? Divide every term by the highest power of x. So it's going to basically say multiply everything by 1 over x squared, or divide everything by x squared. So again, this is just a notational thing. Essentially, we're going to divide everything here by x squared. I could illustrate that by just multiplying by that fraction right there. So what happens when we do this is we get the limit as x approaches infinity, and we have 5x squared plus 8x minus 3, but then each of these are going to be divided by x squared. We also have the same thing in the denominator. We have 3x squared plus 2, and then we're going to divide everything by the highest power of x in the denominator. So that's going to be the first step on the view and example. I looked at the highest power of x in the denominator, which is the x squared, divide everything by that. Everyone okay with what I did there? The reason we did that is when you simplify this, what you end up with is the limit as x approaches infinity of 5 plus 8 over x minus 3 over x squared. And then you're going to still have in the denominator 3 plus 2 over x squared. I just simplified all of those fractions. And now you take the limit of each term independently. The limit of a constant is 5. The limit of all of these rational functions is 0. So we get the limit right here is just going to be 5 over 3, or 5/3. This right here is saying that y equal to 5/3 is a horizontal asymptote. And we see that graphically right here. So back in pre-calculus, the way we said to figure out asymptotes is you looked at the degrees of the numerator and the denominator. So remember, the degree is the highest power of x. So what is the degree of the numerator? 2. What is the degree of the denominator? And if we had the fact that the degree, I'll put this in green, the degree of the numerator is equal to the degree of the denominator, if that was the case, you have to look to the leaders to figure out what the horizontal asymptote is. So if you had that case, remember that all you need to do to figure out the horizontal asymptote or the limit is going to be the leading coefficient. I'll just do LC of the numerator divided by the leading coefficient of the denominator. Notice, what is the leading coefficient? 5/3. So that was the pre-calculus approach. We now technically have a way to compute it without that kind of that weird trick of why do you just look at the degrees? Because the looking at the degrees is really a conversation about the growth of the functions. Which one's growing faster? Well, they're growing about the same, and then therefore you look to the leading coefficients. So let me remind you the other two techniques. Let me go ahead and just do this. I'm going to go ahead and copy them over and give you a few examples because I know we're cutting it close on time. So down here on 7, let's look at this together. The degree of the numerator is what? 1. The degree of the denominator is 3. So this is the case where the numerator is growing slower than the denominator. So what do you think? If the denominator is growing bigger, what is going to happen to the overall fraction? It's going to get smaller. So the answer here is going to be 0. Again, if I kind of show you the whole work for this one right here, let me go ahead and line it up. You can see it right here. My math lab is going to say, go ahead and divide everything by x cubed. And all of this work happens, but whenever the degree of the numerator is less than the degree of the denominator, the limit is going to be 0. The base example there is your reciprocal function because, again, the degree of the numerator is 0, the degree of the denominator is 1, and you have that horizontal asymptote right through 0. So there is 7. On number 8, I have the work right here, but let's look at the degree of the numerator is 8. What is the degree of the denominator, by the way? 5. Good. This one's just not written in descending order, but in either case, the degree of the numerator is greater than the degree of the denominator. This one you do need to be careful with, though. Because if you look at this, notice here that this is positive and this is going to be, let me just kind of call out right here. Notice that the degree here is even, but the degree here is odd. So what if we were to consider the limit of 8b and if we were to consider the limit as x approaches negative infinity? We want to be very careful because the odd and the even will affect the sign of the limit. So if this right here is our function, let's just say it's the same function as there. This one is going to be negative infinity because of the even, odd, negative infinity is going to affect that. But if you looked at this original one, the limit is positive infinity. But still, the growth of the numerator is going to be larger than the growth of the denominator. So you're going to have either something that's going to just grow faster, so it's not going to ever cancel, or it's not going to shrink, it's going to continue to grow, but do be careful with your signs. Does anyone remember what type of asymptote we had in the case where the degree of the numerator was greater than the degree of the denominator? It was the slant or the oblique asymptote. So tomorrow, no, not tomorrow, on Monday we'll do another few examples involving horizontal asymptotes for warm-up, but have a great weekend if I don't see you tomorrow, and I'll be here tomorrow for Flex Day. Have a good day, everyone. Last time we were looking at limits at infinity, and you can see right here we have the limit as x approaches infinity, and it boiled down to 3 cases whenever you're working with limits at infinity. So if you have the degree of the numerator equal to the degree of the denominator, well, then does anyone remember what the limit was? It's just the ratio of the leading coefficients. So again, it's going to be the limit will be the LC of the numerator over the LC of the denominator. So remember that these rules are, these kind of shortcuts, I should say, only work in the context of limits with plus or minus infinity. So don't apply this to everything. It only works when we're considering the limit as x approaches plus or minus infinity. So this is the first case. And notice, again, what we said last time, we can pull the limit inside a composition. So this problem, while there's still that square root, you can go ahead and bring the limit inside of the square root. And we can go ahead and just take the limit of that blue part right there. So because the degree of the numerator is equal to the degree of the denominator, what would be the limit right there in blue? It would just be, okay, good. Let me go ahead and explain it. I was just seeing what you all remembered from last class. So whenever you have the limit as x approaches a positive or minus negative infinity and some sort of rational function, you can see, look at the degree. The degree of the numerator and the denominator are both 1. So the limit is just going to be the ratio of the leading coefficients. So we'll have still the square root, but then it's going to just be 20 over 5. 20 over 5, of course, is just going to be the square root of 4. So it is 2 here. Again, if you go through the MyMathLab homework, it's going to do this little algebraic manipulation where each part of the, or each term is divided by the highest power of x in the denominator to basically create a bunch of reciprocal functions. But of course, if you remember that trick where all you consider is the degrees, that's going to give us a couple scenarios. All right, so in the case of the second one right here, yes, we have fractions, and let's see, 5/3, what is that? That's about 1.67. 8/5, what does 8/5 work out to? I guess a little bit less, so this would be 1 and, come on, lunch, 3/5. So that is 1.6. So this is 1.6. And again, remember that the square root is going to be the 1/2. So I just have 0.5. Basically, I'm just looking at the degrees, and the fractions may make it a little bit confusing, but don't get thrown off of those. So if we look at this, what do we have? Is the degree of the denominator or numerator larger? The numerator. The degree of the numerator is a 1.67, where the highest power of x in the denominator is 0.6. So again, let's consider this scenario where the degree of the numerator is greater than the degree of the denominator. What was the limit in this case? Does anyone remember? So think about this conceptually. Which one is growing faster, the numerator or the denominator? Numerator has a higher power of x. And if you think about it just in terms of like, okay, let's say this was like 2 over 2, but then we had 4 over 3, then we had, let's say, 8 over 4. You can see the numerator is growing faster, and the pattern of these is that this is getting larger. So the limit here is just going to be infinity. So keep that in mind, kind of the conceptual understanding of what's happening with limits at infinity. The other case would be something like, let's say we had like 10b, which would be, let's consider the limit as x approaches negative infinity of x squared minus 1 over x plus 17. Don't ask why 17. It just felt like a good number that was really prime. All right, this is the scenario. Oh, wait, I wanted the other scenario. So let's make that a cube. Let's say x cubed plus 17. That's the third scenario. Does anyone remember the third scenario? What would the limit be for this one? 0. Was that a question or just your?
I do have a question.
Sure, question.
So when we were going over last Thursday, so when
Sure.
the degree of the numerator is larger than the degree of the denominator, the limit is infinity, but how do we know if it's positive or negative infinity or just infinity?
Sure. So let's go ahead and kind of write down those cases. Let me see. Do I have an example here? Oh, 11 will actually answer that question perfectly. So just to summarize the three rules, the degree when they're equal, the limit is the ratio of the leading coefficients. When it is greater, the limit is either going to be plus or minus infinity, and that's the question that you posed. We'll look at that down here below. And then this is the scenario where the limit was equal to 0 because the numerator is being overtaken by the denominator to give you very small values. So any questions on those two examples? Perfect. And then let's go ahead and look at example 11 down here below. So let's consider the two scenarios. We have as x goes to infinity, and we also have when x goes to negative infinity. So the limit as x goes to positive infinity of x squared minus 3 over 2x minus 4. Again, the degree of the numerator is greater than the degree of the denominator. So it's going to be plus or minus infinity, and this one's going to specifically be positive. Yeah. So the negative one is really the one you have to watch out for, and I'll explain why here in a sec. But let's, again, look at graphically what this is saying. So because the limit is equal to infinity, what that means is that as we go to the right, as we go to positive infinity, the graph is going to continue to grow. So you can see graphically, this is continuing to grow, and this, I guess, like purple or pink line is an oblique asymptote. So again, when it was a number, you had a horizontal asymptote. When it's infinity, you have an oblique asymptote. And the vertical asymptotes will happen with one-sided limits. We'll see that later today. But I think the question that you are posing is, well, what about when is it negative infinity? So let's consider the limit as x approaches negative infinity of x squared minus 3 over 2x minus 4. And this is going to start to get to an idea that we're going to explore a little bit more, and it's just paying attention to the signs. So think about what it means to plug in negative numbers. When you plug in negative numbers, you're going to be plugging in values here and here. So think about, let's say you plugged in like a -1 and like a -1. You already know the answer is going to be either plus or minus infinity, so you have to decide which one. When you plug in negatives to something that's squared, what are you going to get? Positives. When you plug in something negatives to something that's linear, what are you going to get? Negatives. So if you're getting positives up top and negatives down below, what infinity are you going to be approaching? You're going to be approaching negative infinity. So again, kind of maybe this will end up being positive when x goes to negative infinity, and this x is going to be negative when x goes to negative infinity. So then you just kind of consider the signs. So does that answer your question? And graphically, we can see what the graph is doing is it's going down. So you can see the graph, if this were to continue, is going to be going down. The limits are the y values, so it's going down to negative infinity. Great. Any other questions on those two kind of thought processes right there? So again, notice that this in this case, notice there's no horizontal asymptote. This is just not a funny problem. Okay, that was funny. No, it wasn't. But there is an oblique asymptote. So what is the oblique asymptote? What we do is consider, let me just go ahead and take our function right here and consider the limit as x approaches, let's just consider the positive one, of x squared minus 3 over 2x minus 4. This is equivalent by dividing the limit as x approaches infinity of x over 2 plus 1 plus 1 over 2x minus 4. So again, you can go ahead and just simply divide. You can use, in this case, you'll need to do polynomial long division to go ahead and figure that out. What's synthetic division work? Would it work with 2? Thinking. You plug in 2. No, 1. So basically, don't stress too much about it in terms of, like, if you don't remember long division, that's okay. But let's say you had like x squared minus 3 over x. You would have this as like x minus 3 over x. So again, know at least your basic division properties. If you don't remember polynomial long division, don't stress about it in terms of the test. But you may want to be comfortable with just standard division rules. So I didn't finish writing this. This should have been a 1 right here. So a little correction. So notice that when you take the limit here, this is 0. This is going, so this part right here, let me write it like this. This part right here is going to go, this part goes to 0 when you take the limit. This part right here that I have underlined, let me go ahead and bold it or highlight it. That part is the oblique asymptote. Y equal to x plus 2 plus, or x over 2 plus 1 is the oblique asymptote. So conceptually, like, yes, we get infinity as the limit, which, yes, that means this is an oblique asymptote. How do you find the oblique asymptote? You're going to have to divide. The limit makes this part go to 0, so the part that does not go to 0 is the actual equation for the oblique asymptote. So you can see that right there. Again, if you don't remember polynomial long division, nothing that involved will be on the test, but again, you may want to review it if something like that shows up on your homework just briefly to keep it in mind. All right, so that, I think, concludes no, it does not conclude, but any questions on this one? Okay, so these questions right here just help the ideas kind of all come together. So I'll do one, and then I'll give you the bottom one to do to see if the idea is stuck. But what we're asked to do is just to kind of make up our own function that satisfies these conditions. You don't need to figure out the formula or anything like that, but let's think about what is this information telling us about the graph? Well, f of 0 is equal to 0. What this is telling us is that this is the point 0, 0 is on the graph. So I'm going to go ahead and put that right there. That point has to be on the graph. This is saying 1, 2 is on the graph. So let's put that right there. And this point is telling us that negative 1, negative 2 is on the graph. So whatever graph I draw, these points need to be on it. What is this telling me right here, though? when I consider the limit as x approaches negative infinity of f of x is equal to negative 1, what is that telling me about the graph? It has a, Emma? Yeah, it has an asymptote, more specifically vertical, horizontal, or oblique. Yeah, because whenever you're considering as x approaches the infinity, this is telling me that I have a horizontal asymptote, y equal to negative 1. But notice this is only when I'm going to the left. So what I have is I'm going to just draw this one over here. Then what about this right here? This is telling me that there's a horizontal y equal to 1, but this one is to the right. So you have this right here. Kind of, oops, not quite. I put that in the wrong spot. It should have been at 1, not 2. It's right there. Once you have that in mind, there's infinitely many answers to this one. Maybe the simplest one would look like something that would look maybe like this. But again, it satisfies the properties of the ones that we were given above. And it was just a little bit of make your own function. Any questions on that one? Okay. So there's the idea. Make sure you go ahead and understand kind of the different scenarios. This one might be a little bit tricky, but let's see what happens. Go ahead and try 13 while I take attendance, and I have a remark on it and something we'll want to watch out for. So let's talk about my answer a little bit here. Maybe a little bit funny looking, but there's one mistake with it we'll need to fix and one thing I want to call out. So 0, 0 is on here, right there. This right here I have in green. Notice I messed this up. Actually, I made 2 mistakes, so let's correct this. This, when we're approaching 0 from the left, it should be negative 1. I had this backwards, so we have something like this right here. And when I approach 0 from the right, I'm going to have something like this. Okay, and notice that I kind of went below I went through the asymptote. That's okay. There's this statement that I think a lot of students get in their mind. It's like, oh, you can't cross an asymptote. That is true for vertical asymptotes because it's an issue with the domain. But technically, asymptotes are concerned with behavior at infinity. So if a graph crosses through a horizontal asymptote, but continues to have this behavior that it gets back to approaching that asymptote and infinity, that's perfectly okay. Typically that'll happen when there's like a square root or something involved. I think we actually even had an example, no need to slide there, but just to kind of give you an equation with one. We had an example, I think, somewhere. Just a little, right here. So you can see right here in number 6, it's not even, it's not even with an absolute value. It's just with this one right here. You see you have a horizontal asymptote. It crosses through that, but it comes down and approaches it. So one thing I just wanted to kind of call out when it comes to asymptotes is that it's okay for a graph to cross through a horizontal asymptote because horizontal asymptotes describe behavior at infinity. So this is okay. There's any questions so far? There's one other mistake that I've kind of made. I didn't draw it explicitly because I didn't want to make it obvious. Anyone think they know what is something I'm kind of abusing here a little bit? I probably should make this. All right, let me do this. What's wrong with the graph now? If that's a closed dot, it's not a function. If you put a closed dot here, realize that would fail the vertical line test. So maybe just to be explicit, put an open dot here to make sure that you do have a function because the graph wanted a function. And I kind of put that hint up there, must pass the vertical line test. So a couple little things just to be aware of that ties together some ideas, but You'll need, I'm gonna specify them as open because again, if this is closed dot down here, then again, it fails the vertical line test. Yeah, because 0, 0 was told that it needs to be on there. So even though the limit, and again, this was just a one-sided limit. So again, just a little subtlety in that. Remember, limits could approach open dots. But this behavior, f of 0 equals 0, is saying that's what's happening at 0. Perfect. How many got something like that? Cool. Very good. So it's some ideas that does take some time to put together. Any other last minute questions on this? Yeah. No, ask away.
Question. So if we were to say the limit is just approaching 0, not from negative or positive, would it technically not exist because as it approaches for both negative and positive, they're not the same?
So, like if this condition wasn't here and this was just the limit as x approaches 0,
Yeah.
then you would just have to do something like this. Something like that, maybe. So you still just need to make sure you have an open dot. What would not be possible if I said like f of 0 is equal to 1 is equal, or f of 0 is equal to 1, because then this right here would be impossible because that wouldn't be a function. So the whole is important on this one. So
Sorry, I was just
no, good questions, great thoughts. Because again, this is the culmination of chapter 2. All these ideas come together in basically 1 or 2 examples. So there's one more idea that we need to explore in chapter 2, and that is with vertical asymptotes. It's really just, we already saw them visually. So you can see as x approaches 0 from the right-hand side, the graph goes up. So if we have this, that's this first scenario. If x is approaching 0 from the right-hand side, the graph is going up to positive infinity. But consider as x approaches 0 from the left-hand side, the graph is going down to negative infinity. So we do have this scenario where the limit does not exist, but we still can describe the behavior in terms of plus or minus infinity. So the scenario right here is we have the limit does not exist. Like if you tried plugging in 0, notice you get 1 over 0. And 1 over 0 is not an indeterminate form, so there's no factoring or canceling possible here. Because remember, if it's 0 over 0, try factoring and canceling. But because this cannot factor and cancel, this is the scenario we have vertical asymptotes. So limits, when you have something where you get a 0 in the denominator and there's no factoring and canceling, gives you the vertical asymptotes. So the line x equal to a is a vertical asymptote of the graph of a function if either we have the limit from the right going to plus or minus infinity or the limit from the left going to plus or minus infinity. So horizontal asymptotes come from when your x is approaching infinity and you get a number, reverse that for vertical. Vertical asymptotes come from when you're approaching a number and you get infinity. So find the limit. Well, this is a little bit tricky because what should you always try to do when you find a limit? You should always just try to plug it in. If I do that, I get 1 over 1 minus 1, which is 1 over 0. 1 over 0, okay, it's not indeterminate, so I can't factor and cancel that. But what this tells me right here is that we have, or I'll just do it again, arrow. So there's a vertical asymptote at x equal to 1. That's what it told me. But I want the limit. So I need to consider now, is it plus infinity or minus infinity? So this also follows that so I'll write it down here and change the color. So L is equal to plus or minus infinity. And we have to figure out which one. The way we figure that out, pick a value near x you're approaching. So I'll just say here, so to figure out, check a value near. Don't just pick any because you want to make sure it's close so it grabs the asymptotic behavior. In this case, we'll just say x I'll say near 1, which is the value we're looking at here, on the right. So what we're going to do is just don't text, they could wait. Test let's just say like 1.1. Text 1.1, are you positive? Yeah. Anyway, that was weird. Anyway, so test x equal to 1.1. And let me specify, it needs to be near it. If it's not near it, then you may get the wrong sign. So what I'm going to do is I'm going to do 1 over 1.1 minus 1, which is 1 over 0.1, which, again, you can compute that. But look at this, the same thought process we thought about earlier. The numerator, positive or negative? Denominator, is it positive or negative? Positive over a positive is, so this is then positive over a positive, which is going to be positive. And again, I don't care about the number because again, this is not, the limit is not 1 over 0.1, that's just a test value. So what this means is, so L is equal to positive infinity. And this positive is coming from there. Because we already figured out that it was a vertical asymptote based off of our work up here. This down here is just to determine the sign, whether the graph was growing up or growing down. And again, if you had an idea of the graph of this function, this is just going to be, there's going to be a vertical asymptote at x equal to 1, and then this function is going to be in the first and the third quadrants. So you can see when we're approaching 1 from the right, we're looking at this behavior up in this first quadrant. All right. So again, 15, I'm going to go through it a little bit faster so the ideas kind of are more fluid. Step 1, try plugging it in. You get 1 over 1 minus 1, which is 1 over 0. What this tells me is that there's a vertical asymptote, namely x equal to 1. We already see that down here in this graph. So because of that, the limit is equal to either plus or minus infinity. We have to figure out plus or minus. Test a point on the appropriate side. So let's go ahead and test x equal to, what do you all recommend? 0.9 is probably a good choice. It's pretty close, not too crazy of a value. And if you go ahead and then test that, you get 1 over 0.9 minus 1. You get a positive 1 over a negative 0.1. So you get a positive over a negative. A positive divided by a negative is negative. So L is equal to negative infinity. That's how vertical asymptotes appear with the context of limits. Any questions on this one? So in the case of 16, we're going to go ahead and consider a few other scenarios. Do they do coffee delivery now? I'll be right back. I got a text. I'm just... So in the case of number 16, coffee sounds so good right now. I have half a cup left up in my office. Anyway, focus. So 16, still limit. What are we going to try to do? Plug it in. Every time I ask, just plug it in already. Okay. So we get 2 minus 2 over 2 squared minus 4. Oh, that should be squared. So we get 0 over 0. If we get 0 over 0, what should we try to do? Factor there. So what we're going to end up with is, oh wait, do I get 0? Oh no, I was thinking plus. We don't get 0. Do we get, oh, yeah, we. 0, 0. Okay, yeah, I'm thinking coffee now. Told you I need some. So okay. 0 over 0, let's factor and cancel. So we get x minus 2 squared over an x minus 2 times an x plus 2. The squares cancel. So this, or not the square, but the minuses cancel. So I end up with now the limit as x approaches 2 of x minus 2 over x plus 2. Now when I plug it in, what do I get? I get 2 minus 2 over 2 plus 2, which, yes, 0 over 4, which is 0. So notice that that is not a vertical asymptote here. So again, just keep that would technically be a hole in the graph. So keep in mind, don't just automatically start thinking like, oh, I got to test points. Keep in mind the context. First test plugging it in, and then if you get 0 over 0, factor and cancel and see what happens. So let's skip 17. 17 is going to be very similar to this last one. If you want to try it out, it's 1/4. It's going to be very similar to that 16. Just make sure you plug in, factor, and cancel. Let's look at 18 now. If you look at 18, when you plug it in, you get 2 minus 3 over 2 squared minus 4, which is going to give you minus 1 over 0. So my recommendation is still to go ahead and factor. The reason I still recommend to factor is because it's easier to go ahead and test a point. So notice, okay, yeah, I see that there is a vertical asymptote here. So there is a vertical asymptote, x equal to 2. But I'm still going to go ahead and recommend, go ahead and just factor the denominator as a difference of squares, because it's easier to plug something into that. Let's test a point. Remember, x is approaching 2 from the right, so what's a good point to test? Let's test x equal to 2.1. So in this case, what I'm going to do is, let's see, we get 2.1 over 2.1 plus 2, and then 2.1 minus 2. And we get a positive in the numerator. We get a positive times a positive. So you could go through those computations, but honestly, we already know because of this, L will either be plus or minus infinity, and we're just trying to figure out which one it is. So if we have a positive divided by a positive times a positive, what should we get? Positive. Question, yeah.
Are we supposed to subtract 3, so wouldn't the numerator be
Oh, I forgot that up there. So let's make this correction. This should be 2.1 minus 3, which would give you a negative, which would make this a negative. Good catch. Thanks, Emma. So what is the limit? Negative infinity. And then checking the rest of my computations, 2.1 plus 2 is a positive here. This is going to be a positive, and that will be a negative. So we do get a negative divided by a positive, which is indeed going to be negative infinity. Any questions on that one there? Awesome. If we look at 19, we have a very similar problem, same function, just from the other side. Go ahead and check out that one. Let me give you a moment to try it out first. I just want to see what I have left and see what other things we need to cover before the day ends. So up on the screen is the work associated with 19. Just testing a point from the left-hand side. Anyone have any questions on 19 or anything associated with these vertical asymptotes? Okay. Then let's look at the next page. Does anyone need more time here? Okay. Then on 20, notice it's the same function as the previous page. So notice it's the same function as the ones we did up here. So there's the left-hand limit, or excuse me, the right-hand limit. There's the left-hand limit. And remember, this notation just says consider both sides. So if you consider this one, yes, you get negative 1 over 0. We saw that on the last two exercises. So what we would do if we had a two-sided limit is just check the one-sided limits. And we did this, see 18 and 19 on the previous page. Since the one-sided limits differ, the two-sided limit does not exist. So what we would simply say here, we wouldn't say this. What we would simply say is this limit, the limit does not exist. So if you ever have a scenario like you can't factor and cancel, what you will do is check the one-sided limits. For the sake of time, I'm going to just go ahead and put up the work for 21. I'll leave it to you as an exercise after class. But here's the work for 21. Notice that when you look at 21, you get 0 over 0, so you still try to factor and cancel. But because it's a two-sided limit, you still end up having to check the one-sided limits. But because the one-sided limits are the same, you can say that the limit to this one is the associated matching one-sided limit. So I'm going to leave that one as a little bit of an exercise to you. There's really nothing new into that one apart from the ones we just did. On 22, it's a very similar exercise to what we did before, where we're asked to sketch the function. Again, keep in mind it must pass the vertical line test that satisfies these conditions. So what's new right here is this right here. On the right, notice that this one is going to give you a vertical asymptote of x equal to 0. So let me give you a moment just to try this one out yourself. Again, it puts the ideas together from all of 2.6. So after you do this, we'll then talk about a few special cases with asymptotes, and then that wraps up chapter 2. So here's one possible answer. Again, yours might differ than mine. But again, if we look at each apart, f of 0 is equal to 0. Interestingly, this goes through the vertical asymptote. In order to deal with that, if you were to actually write an equation for this, it would probably be a piecewise function. I had never thought about that before until I was writing it up now, but because this is a scenario where you have an asymptote going through x equal to 0, in order to do that with an equation, it probably would have had to been a piecewise function. So just to clarify, like kind of the context, like, a graph can never go through a vertical asymptote. Well, if you have a piecewise function, you could put them together to allow that certain behavior. But you can see as x approaches 0 from the left, it goes down. As x approaches 0 from the right, you get some value. We have an open dot, so it passes the vertical line test. But does anyone have any follow-up questions on 22? And again, your solution may differ, but as long as you put together the ideas from the section, you should be good. The last three scenarios where asymptotes really will show up would be in the context of exponential and trigonometric functions. And there's really no trick on these. You just need to know, properties of the functions. So like if you were, for example, asked in this first one, find the limit as x approaches, let's say, it's saying infinity of ln of x, you have to really kind of just know that the graph of ln of x, you could plug in values, but it's going to grow without bound. And if you were to consider, so it's not explicitly asked here, but if you were to consider the limit as x approaches 0 from the right-hand side of ln of x, what would be the limit as x approaches 0 from the right-hand side of ln of x? It's not going to be 0, because if it's going down, it's going to be negative infinity. So some of this does just come down to there's no tricks apart from plugging in values or knowing what the graph of the function is. So Most of our examples in this section have been polynomial or rational functions. So keep in mind that we do have some other functions in our library that we can work with. Same idea with 24 and 25. In 24, we're considering the secant function. I have this graphed over here, but hopefully you know, or you're able to reason through where are the asymptotes for the secant function. They basically come where the zeros of the cosine function. So you can see this right here is pi over 2. When we approach it from the positive side, what would be the limit? It's going down, so the limit would be equal to negative infinity. And same with tangent. Tangent occurs where, just remember that tangent is sine of x over cosine of x. So therefore the asymptotes are occurring at the zeros of cosine. So in this case, the limit as x approaches pi over 2, so we're going to pi over 2 of the tangent function. When I approach it from the right, the limit is equal to negative infinity. So these last few examples just illustrated that, hey, you're just going to need to have information about these functions in the back of your mind as you go through them. Does anyone have any questions about section 2.6? Perfect.